Well, here we are already at the fourth video. We are picking up steam now, and by the end of this one, we'll be able to take the derivative of any polynomial whatsoever. The main intellectual interest here is not just the final result, i.e. what is the derivative of a given polynomial, but rather the process by which we obtain that result. As you know, a polynomial is an expression such as this. It's a sum of so-called monomials, those are these individual terms, which themselves consist of some constant multiple of some power of x, or whatever the relevant variable is. The constant multiples, the so-called coefficients, can be any real numbers whatsoever. They don't have to be whole numbers like 8, 7, or 10. It could be square root of 2, or pi, or 4/13, or whatever you want. The powers of x, though, have to be whole numbers. Fifth power, second power, first power, and even here there's an implicit zeroth power since x to the 0 is 1. But no negative powers, no fractional powers, no irrational powers, nothing like that. Anyway, if I asked you to try to come up with the derivative of this particular function, at this point there's nothing you could do except to try to grind it out from first principles, which would actually work, though it would be quite a slog. What we're going to do instead is to take our faces away from the page, get some distance from this problem, and try to come up with a way of finding the derivatives of all polynomials at once. We're going to develop a two-part strategy for finding polynomials' derivatives. The first part is to figure out how to take the derivatives of all monomials. And once we've determined that, we'll prove a theorem that will tell us how to find the derivative of a sum of functions whose derivatives we know individually. That way, if I know the derivatives of these individual monomials, I'll be able to call on that theorem and say, well, I can figure out what the derivative of the sum will be. And that structural theorem is something that we will be able to use far beyond this particular problem. For example, once we have figured out the derivative of the sine function and the logarithm function, we'll be able to use that structural theorem to immediately determine the value of the function sine x plus logarithm x. Anyway, now you know our two-step strategy for finding the derivatives of all polynomials. The specific task of finding derivatives of monomials, and the structural task of figuring out what the derivative of a sum looks like. It turns out that the first of those two tasks, the specific one, can itself be broken into a two-step process. Every monomial, after all, has the form c times x to the nth power. First, we will figure out what the derivative of anything of the form x to the n looks like, and then we'll prove a little structural theorem, which will tell us how to take the derivative of any constant multiple of a function whose derivative we already know. And again, that structural theorem is something we will be able to use in the future. That way, to return to my earlier example, once I know the derivative of sine and the derivative of the logarithm function, we will also be able to take the derivatives of functions like 3 times sine x and 7 times logarithm of x. And then, using the other structural theorem I mentioned, we'll be able to take the derivative of their sum as well. And this actually initiates a theme that we're going to see in the next few videos. We're going to learn to take the derivatives of very specific functions, like x to the n, or sine x, or logarithm x, or whatever, and then we will learn structural theorems that will help us find derivatives of combinations of the specific functions. And by the end of chapter 2 in the book, we will know how to take the derivative of pretty much any function built up from the basic pre-calculus functions that you know and love very easily. All right, so now you know the full strategy for taking derivatives of polynomials. The core of the whole argument is going to be how to take the derivative of x to the n, this very specific function, and then we will prove those two structural theorems. Okay, let's get started. Our problem is to find the derivative of x to the n, where n can be any whole number. At this point, the only thing we can do is to appeal to first principles. So we start by noting that the derivative of x to the n can be rewritten just as we did in the previous video by taking this function and tucking it back up into the top, like so. So now instead of having our derivative operator, as we talked about last time, we are thinking about this as an actual ratio of infinitesimal changes. And remember how that works. We're nudging the function's input, and that change in input begets a change in output. And when we expand that change in output, that's just going to give us the output after the change to x plus dx minus the output prior to the change, when the input was just plain old x, so that we end up with x plus dx to the nth power minus plain old x to the nth power. All that's upstairs, and downstairs is still just dx. So far, so easy. This is exactly what we did when we found the derivative of x squared last time. Well, what did we do then? When we had 2's here instead of n, we just expanded this and we had some nice cancellation, and that was the end of the game. We ended up with the derivative of x squared being 2x. So you might say, well, let's just do the same thing. Let's just expand this out, and all's well. Ah, there's the rub. We know how to expand this out if the exponent is 2, and it's not hard if it's 3 or 4 or any specific value. But how do we do it in general when the exponent is left as just plain old n? Well, you might know the binomial theorem, and if you do, you can expand it that way, but it turns out that we don't even need that. But we will have to put this on pause for a moment while we review something from algebra. So let me section this off for a bit, and we will spend some time down here in the algebra dungeon. Let's say we have a product like this. How do we multiply it out? Well, you can do it either very patiently, doing one distribution after another, or you can do it all together if you're careful. And the way you multiply it all out together is to recognize that after you do all the distribution, this stuff is going to be equal to the sum of a whole bunch of terms. Those individual terms will be products drawn from these different groups. As I discuss in the book, I like to think of those products as the results of handshakes, though they are weird three-way handshakes. I guess that would be 3 people in a little ring. And in each three-way handshake, there would always be one member from this group, one member from this group, and one member from that group. You consider all the possible three-way handshakes, where handshake corresponds to multiplication, and then add up all the results. So for example, one way to do it would be A from this group, M from this group, and S from that group. And that would give you the product AMS. The American Mathematical Society. That's one handshake, but we have to consider all the possible handshakes with one representative from each group. So for example, we could also have A, M, and T, and we would end up with AMT, which we have to add on to the previous term. And on and on and on we'd go. We've exhausted the possibilities that involve A and M, but we could have something like A, N, and S. And so over here, we would get another term, A, N, S. And then A, N, and T. There's our infinitesimal ant. And now we've considered all the handshakes involving A, because we had A, M, and both possibilities there, A, N, and both possibilities there. So we could move on to B, and have things like B, M, S. And I'm not going to spell each one out, except to say that there would be a total of, let's see, 3 times 2 times 2, 12 terms altogether. Ultimately, the product would look like this. Every Algebra 1 student, of course, learns this in the special form where you just have 2 binomials, and it's often taught by the acronym FOIL, first, outside, inside, last. That's just counting up handshakes. It's a special case of this general principle. And the general principle is nothing deep. It's just using the distributive property over and over and over again. Anyway, bearing this handshaking business in mind, we can return to our expression and make some progress. X plus dx to the nth power. What does that mean? Well, n, we have said, is a whole number. A whole number exponent just represents repeated multiplication, so that this expression simply means x plus dx times x plus dx times x plus dx times x plus... We multiply it by itself n times, whatever n might be, whether it's 3 or 42 or 6 million. Now, how do we multiply something like that out? Well, of course, we play the handshaking game, which might look like a hopeless task, because we would end up with 2 times 2 times 2 times 2, 2 to the n terms, which of course becomes huge very quickly. Even if n is only 10, that's 1,024 terms. But as you'll see, we don't need to write down all of the terms. Once again, our infinitesimals will help us. Let's think about some of the terms that we will get. We're going to have these not 3-way handshakes, but n-way handshakes. Each handshake is going to be a big ring with someone from this group, someone from this group, someone from this group, all the way down to someone from that group. All different possibilities there. Well, what's one possibility? We could take the x from this group, and the x from this group, and the x from this group, and the x from every intermediate group, and the x from that group. Every group sends its x to the handshake. And if we do that, we end up with the term x to the n. That's going to be one of the many, many, many terms that we will get. Good. Let's identify some more terms that will be in here. Instead of every one of the n groups sending its x, let's say that one group decides to be rebellious and sends its dx, and all the other groups, all the other n-1 groups, send the x. So for example, we would have a handshake where we'd get the dx from the first group, the x from the second, the x from the third, the x from everybody in the middle, and the x from the last one. So who would end up in the handshake? we would get one copy of dx and n minus 1 copies of x, so that our next term would be x to the n minus 1 dx that we got from the first group. But wait a second, we're actually going to see that term many times, because I described this one as the dx coming from the first group and every other group sending their x's. But one of the other handshakes is going to be where the second group sends its dx and every other group sends its x, which means we would have another term that would look like this. Well, of course, it's not just going to be those two. We got this one when the first group sent dx and everybody else sent their x's, and this one when the second group sent dx and everybody else sent their x's. How many terms like this will we have? Well, we'll have another one where the third group sends a dx and everybody else sends an x, and all the way down until finally the nth group, the last group, sends the dx and everybody else sends an x. So how many of those will there be altogether? There will be n of them, because there are n ways to choose the group that sends the dx along. So rather than writing this down n separate times, we know we're adding all these things together, so let's just say we add in n copies of this. So I'll rewrite that as n copies of x to the n minus 1 dx. And of course that's going to be added to that first term. Okay, that's progress, but you might be thinking, well, we still have a long way to go. There are many, many, many more ways to form those handshaking groups. But stop and think about what every other handshaking group has in common. This one was when nobody sent a dx. They all sent their x's. Each one of these, all n of them, those came when only one group sent a dx. Every other possibility is going to involve at least two groups sending a dx. And if at least two groups end up sending a dx, the product is going to involve a higher order infinitesimal. So long as there are at least two dx's in a handshake, we know from our work last time that that product can be counted as a 0. And that means this is it. We don't have anything else to write down, because all the rest of the stuff is higher order infinitesimals, and those are treated as zeros. Isn't that nice? Well, it gets better, because now let's return to our actual project of taking the derivative of x to the n. We've just seen that when we expand this term, we are going to end up with this stuff, which is just what we found down here. And of course, we still have to subtract off the xn and divide by dx. Well, now look at what happens. We have some cancellation. X to the n and minus x to the n. Those cancel out, leaving us with n x to the n minus 1 dx upstairs and dx downstairs. And of course, those dx's cancel, leaving us with n x to the n minus 1. Aha! This is the result we sought. Please be sure you understand why every one of these equal signs is justified. But for now, let me just summarize the result. We have just proven that for any whole number n, the derivative of x to the n is nx to the n minus 1. And this very important result is often known as the power rule. And I should point out that it is really a preliminary version of the full power rule, because we want to consider cases later where our function x to the n has an exponent that is not a whole number, like x to the minus 1, the reciprocal function, 1 over x, or x to the 1/2 power, which is the square root function, or for that matter, just x to the pi power. Does this power rule still hold in those cases? We shall see. But for now, we have this very nice preliminary version. And when you memorize it, don't just think of this sequence of symbols. Or think of the symbols, but think of them almost like living creatures. Think of what happens to them. You've got your function x to the n. When you take its derivative, the exponent n falls down in front of it, there it is, and in its place, the exponent actually gets reduced by 1 to n minus 1. So for example, if we were looking at the derivative of x to the 5th, well, that exponent 5 goes down in front, and in the derivative, the exponent is reduced by 1, so that we end up with 5x to the 4th. Similarly, the derivative of x to the 8th is going to be 8x to the 7th, or the derivative of x to the 42nd power is going to be 42 times x to the 41st power. You start to see how powerful this power rule is. We've proved infinitely many cases at once. That is, of course, the glory of algebra. And of course, even though we used the Leibniz notation to derive this result, we can express it in prime notation as well. For instance, we could say that if f of x is x to the 19th, then f prime of x is 19 times x to the 18th power. All the usual variations are possible here. If y is x to the 108th power, then dy dx is 108 times x to the 107. You get the idea. Maybe the last thing I'll note is that this power rule contains within it the result that we proved last time, namely that if we're looking at the squaring function and we take its derivative, well, of course, what we will get, we know it's going to be 2x, but just to see that it sits with this, the 2 comes down in front, and we reduce that exponent by 1, which would just leave it as x to the 1, which of course we would just write as x. So that's our old friend from last time. All right, you get the point. The power rule is very, very easy to use, but be sure you understand the argument we use to prove it. It's such a lovely argument that it would be a pity if you went through your calculus class without stopping to appreciate it. All right, now that we've got our power rule, let's take stock of where we were in our general strategy. We were trying to figure out what the derivative is of any monomial. And then once we had that, we were going to prove a structural theorem about the derivative of a sum of functions. And putting those two pieces together would give us enough information to take the derivative of any polynomial. Well, we're almost through the first task. We know how to find the derivative of x to the n for any whole number n. But we're looking for the derivative of any monomial, which is not just x to the n, but it could have some constant coefficient as well. And while it would actually be pretty easy to figure out the derivative of such a thing from first principles, let's be a little more abstract. And as I suggested before, we will prove a structural theorem where we're not just looking at a constant multiple of x to the n, but instead we're looking at a constant multiple of any old function, because we want to be able to use this structural theorem in places beyond the task at hand. We want to be thinking towards the future. These structural theorems we're going to be proving are generally known as the linearity properties of the derivative. There are two of them, and the first refers to the derivative of a constant multiple of a function. That is going to be, well, we shall see. And the second linearity property refers to the derivative of a sum of two functions. We'll see what that will be in a moment too. So how do we actually derive formulas for these things? It's actually very, very easy. We just go back to first principles. Let me section some space off for myself down here. And we'll start with this first expression, the derivative of a constant multiple of a function. Let's start by rewriting this as a quotient of infinitesimals, as we have done many times before. Now you know the drill. We're going to expand the numerator. This is the infinitesimal change in this function's output. But remember, it's not just the function f, it's the function c times f of x. But it's the same old story. We want to compare the output of this expression after the change, that is, when the input is x plus dx, with the output of this expression before the change, which is when the input is x. So when we do that expansion, we end up with this. Here's the output of the expression after the change, and here is the expression prior to the change. And now you might say, well, I'm stuck because I don't know what f is. F is just some general function. That's okay. We can still massage this thing algebraically a little bit. We can factor this c out of the numerator. And in fact, we can pull that c out of the whole fraction so that our expression looks like this, with the c out in front. Well, wait a second. All this stuff in the parentheses looks very familiar. This whole thing is our recipe for computing a derivative from first principles. If you don't see that, just collapse the top into a simpler expression. That is going to be the infinitesimal change in f of x. Read this backwards and you will see that immediately. And now we could take this and rewrite it in the usual way to emphasize the derivative operator. And we have reached something interesting. I'm going to put the final result up here as one of our linearity properties. This equality is telling us that when we have the derivative of a constant multiple of a function, we can just pull that constant through the derivative operator, which is what we end up with over here. For example, what's the derivative of 5x squared? Well, that's easy, because this is a constant multiple of a function whose derivative we already know. So we can pull this 5 through the derivative operator and end up with 5 times the derivative of x squared, which we know is 5 times 2x, and hence 10x is the derivative of the function we started with. Or to take another example, what's the derivative of minus 3x to the 5th? Well, this is a constant multiple of a function, so let's pull the minus 3 outside of the derivative, like so. We know the derivative of x to the 5th, that comes from our power rule. It's 5x to the 4th, so the derivative of this function is ultimately equal to minus 15x to the 4th. And one more, let's do a pretty general statement here. If f of x is c times xn, so we are considering a general monomial here, then what can we say about f prime x? Well, by our first linearity property, the c just sits there as a constant multiple of x to the n's derivative, which we know is nx to the n minus 1, thanks to our power rule. And let me rewrite this by associating those two factors like this. This little thing that we've just proved right here is something you'll end up using all the time. Again, try to read it not just as a sequence of symbols, but as a more dynamic interaction among the symbols. We start with a monomial. To take its derivative, the n comes down and combines with the c to give us their product, cn. And then, of course, the exponent drops by 1. If we bear this result in mind, we can take derivatives like these ones even faster. For example, what's the derivative of minus 9x cubed? It's minus 27x squared. The 3 comes down and multiplies with the minus 9, and then we drop its exponent by 1. Or, what's the derivative of 20x to the 5th? All at once, that's going to be 100x to the 4th, the 100 being the product of the 5 and the 20. Good. So taking derivatives of monomials is easy, thanks to the power rule on one hand and this first linearity property on the other. And that completes the first stage in our two-step process for finding the derivatives of polynomials. The second stage is to establish this second linearity property. If I take the derivative of a sum, what do I get? This property is just as easy to come up with as this one, and the result is exactly what you might hope it is. The derivative of a sum of functions turns out to be the sum of the two functions' derivatives. The proof of this second linearity property is just as easy as the proof of the first one, so I will leave it for you. Try proving it on your own, and then compare your work with the proof that I give in the textbook. All right, we now have all the pieces of the puzzle, the power rule and our two linearity properties. By the way, these sorts of linearity properties are not unique to the derivative. Later in the course, we will see linearity properties of the integral, and we have linearity properties of infinite series, which will come later still. And linearity properties, these two specific patterns that apply to various operators, where you can pull constant multiples through and split up sums into two parts like this, are themselves so common that there is a whole subject, linear algebra, which is built upon them. But that is a story for another class. Our goal here was to be able to compute the derivative of any polynomial we might ever meet. Let's do one example slowly and then another one more rapidly. Here's a third-degree polynomial, and we want to take its derivative. Well, if we tried to do this from first principles, we would succeed, but it would really be a pain. Instead, we can use the stuff we have proved in this lecture. The first thing to recognize is that the function whose derivative we want is a sum of smaller functions. You might say, well, there's a difference in there. It doesn't matter. A difference is a sum. Just this once, let's make that explicit and rewrite that as plus minus 5x squared. Every subtraction is, of course, just the addition of a negative. So now we have 1, 2, 3, 4 monomials, and they've all been added together. Well, our second linearity property tells us that the derivative of a sum is the sum of the derivatives. So the derivative of this sum is the sum of the 4 individual derivatives. But now each one of these 4 derivatives is something I know how to compute. The first one, the derivative of 3x cubed, is 9x squared. Then the derivative of minus 5x squared is minus 10x, of course. What about the derivative of 3x? What's that? Well, you could think of that as 3x to the 1, and that's going to give you 3x to the 0, which is 3. But that's sort of a tortured way of coming up with the derivative of something that you should be able to see geometrically in a second. The graph of the function y equals 3x is a line whose slope is 3. That means for any value of x whatsoever, of course, the local slope is 3 because the global slope is 3. That means the derivative of 3x is just the constant function 3. Which leaves only our last derivative to take, the derivative of the constant function 2. Well, what's the derivative of a constant function? Think about it geometrically. The graph of any constant function, such as y equals 2, is a horizontal line. That means for any input value of x, the local slope is 0. So of course, the derivative of any constant function, whether it's y equals 2 or y equals 17, is 0. Clean this up a bit, and we get 9x squared minus 10x plus 3. And our work is done. Now, I spelled out every little bit in this first example. In practice, one takes the derivative of a polynomial just by writing it down all at once. For example, If f of x is 8x to the 5th plus root 2x squared plus 7x plus 10, which may look familiar because this was the polynomial I wrote down in the first minute of this video, then its derivative, f prime of x, is, let's see if we can just write it down in one shot. We know we can take derivatives term by term, thanks to our second linearity property. So the first term's derivative is 40x to the 4th, and to that we'll add the second term's derivative, which is going to be 2 root 2x. What's the derivative of 7x? Well, that's the constant function 7, because this is just a line with global slope 7. And what's the derivative of the constant function 10? Well, as we said a moment ago, the derivative of any constant function is 0. So plus 0, which I'm not even going to bother writing on in black ink. And so we are done. If we had tried taking the derivative of that thing from first principles, we probably would have been busy for 20 minutes, checking and rechecking our work as we had to do things like expand x plus dx to the 5th, and no doubt making arithmetic errors along the way. But thanks to these few little theorems we proved, we were able to write down the derivative of this function in a matter of seconds. Let's do one more example. If y is 3x to the 4th minus 2x cubed plus 5x squared minus 9x plus 52, then y prime, the derivative of this thing, is going to be 12x cubed minus 6x squared plus 10x minus 9. The end. After you've done a few of these, you really can write down the derivative of any polynomial pretty much as fast as you can write, period. Okay, let's do one last example so that you can exult in your newfound powers. If f of x is 4x to the 4th minus 3x squared plus x minus 22, find f prime of x. Now take a minute to pause the video and write down the solution on your own. All right, did you get it? The actual derivative is 16x cubed minus 6x plus 1. Good, and note that by having this function here and its derivative, we can answer various questions about the graph of f, even though I can't see it. God help you if you want to try to graph a 4th degree polynomial by hand. But of course we know it has some graph, we just don't know what it looks like. Maybe it looks something like this, or maybe like this. We could get some information by thinking about this more carefully, but let's just ask ourselves one question. What does this graph look like where it crosses the vertical axis? Well, we know that happens when x is 0, so we could find the point where it crosses the vertical axis by looking at the equation for f. Well, f of 0 is 0 minus 0 plus 0 minus 22, so f of 0 is minus 22. That means the graph of f passes through the point 0 minus 22. But let's say my interest is not just in where it crosses the axis, but how does it cross the axis there? Is it increasing as it goes through? Is it decreasing as it goes through? If it's increasing, is it increasing rapidly? Or is it increasing slowly as it crosses through? If it's decreasing, is it decreasing slowly or decreasing rapidly as we go through? Or is it just moving along at a horizontal line there? And when I say there, I really just mean the infinitesimal neighborhood, the local neighborhood of x equals 0. What's going on as it crosses through there? Well, we're asking a question about the local slope of the graph there. Well, the local slope is the derivative. So this is the function for the derivative, and we want to know what's happening when x is 0. So f prime of 0 is the thing we're interested in. Well, if you pop 0 into this, you end up with just 1. F prime of 0 is 1. What does that mean graphically? It means that the local slope of the graph of y equals f of x is 1 when x is 0. The graph is passing through that point with a slope of 1. It's increasing as it's passing through there. This is a good place to stop because we have come a long way. Congratulations! You can now take the derivative of any polynomial whatsoever. And we have progressed quickly. After all, in the previous video, it took us almost the entirety of the video to come up with the derivative of y equals x squared. Now we can take the derivative of any polynomial whatsoever. Be sure you read the end of chapter 1, which includes some types of problems that I'm not discussing in these videos. We will move on into chapter 2 next, and by the end of that chapter, you'll be able to take the derivative of pretty much any function someone might throw at you. But make sure you are doing all the exercises in the book, because that's where you're going to get reinforcement on the notion of what a derivative is all about. You need to be able to think about derivatives, not just take them. And the only way to get comfortable with that is by doing lots of exercises, some of which will be mechanical, like actually cranking out derivatives, but most of which are going to be conceptual, or just getting used to the notation. You might think you're getting it just by listening to the videos. You aren't. You've got to do the exercises. All right, end of little sermon. We've come a long way, but we have a long way to go. Do your homework, and I will see you next time. I guess strictly speaking that's not true. Maybe I should say, and you will hear me next time. Either way, goodbye.